100th anniversary of Einstein's general theory of relativity. So a little demonstration here at home to explain the essential ideas. So Einstein wants to know how the force of gravity works, how the sun communicates the pull of gravity across empty space to the Earth. Here's the idea he comes up with. He says that the fabric of space is nice and flat if there's nothing there, no stars, no planets, which would mean that if an object rolls through that environment, say this is a comet or a planet, it will go in a nice straight line trajectory. But the key thing is Einstein says that if we have a heavy, massive object like the sun, Einstein says that the sun, merely by being within the fabric of space, causes the fabric to curve, to warp. And then other objects, like the planets, the Earth, Mars, and so forth, he says, they go into orbit because they're rolling along the curved environment that the sun creates. This, according to Einstein, is how gravity is communicated from the sun to the Earth, to Mars, to the other planets. This is how gravity works. Now, we did a little version of this demonstration not too long ago on the Late Show with Stephen Colbert. We got a lot of really great response and a number of great questions were asked online. So let's answer the two most frequent questions that people asked. Okay, question number one, Alec.
Why isn't the Earth spiraling into the sun?
Yeah, exactly, right? When you look at the marbles, they're all spiraling into our yellow shot put here. So would that happen to the Earth? Why doesn't the Earth spiral into the sun? Well, the answer is these marbles are spiraling in because they're losing energy, because of their frictional interaction with the spandex. In empty space, there's virtually no friction at all, so planets hardly lose any energy. Now, they actually do lose a little bit because the planets can cause the fabric of space to ripple a little bit. We call it gravitational radiation. So if you were to wait about 10 to the 20 years, 100 billion years, if the Earth is still here, it will, in fact, spiral into the sun. Very good. Second question, Sophia.
Isn't it gravity that pulls the yellow things down?
Yeah, right? So if you think about it, the reason why our yellow shot put sun is causing the spandex to warp, it's because gravity is pulling on the shot put, right? So we're kind of using gravity to explain gravity. But the key idea is that Einstein says that the sun, merely by virtue of being in space, causes the fabric of space to warp. That's the key idea at the heart of the general theory of relativity. All right, guys, so that's all for today from the Day Greene Science Lab. Science at home?
Yo!
All right, see ya. You know, there's this interesting argument by your colleague at Oxford, Nick Bostrom. Do you know Nick? He's in the philosophy department.
Oh, go on, yes. Okay.
Yeah, and you know, I wrote a little bit about this, so I got some feedback from people, which was a little bit surprising. And he argues that the notion of a simulated universe, that, you know, the matrix, if you will. Imagine one day we have these powerful supercomputers, and we really, with fantastic fidelity, can create a universe in silico, if you will, which has sentient beings within it that don't know that they are in a simulation. And he goes through an interesting argument with, just for brevity of time, let me just simplify it. He may be a little irritated with the simplification, but it gets to the main point, which is, it's so, in principle, easy, once you have that technology, to create a simulated universe, that there'd be many more simulated universes than real universes. Real universes are hard to create. Maybe there's one, maybe there's a few, but it's hard to imagine that you could create them in as great abundance as you could create universes in a computer. You come home at night, you flick it on, you create a universe, you sort of kick back and you watch what happens. So he argues that it's therefore much more likely, just based on the statistics, that we are in a simulated universe than that we're not in a simulated universe. So I wrote about this in a book that spoke about various ways in which you can imagine other universes. So the surprise for me was people came back and said to me, and then Nick, I read later, people said to him too, this for them was the most convincing argument for a creator. Because now the creator was not some mysterious being. It was some futuristic teenage kid with pimples in his garage who just created the universe. So, my question to you, what do you think about that?
I can't see how you could refute it. I mean, I can't see how you would actually be sure that we're not
If a religion were to rise up, where people were honoring the teenage kid, would you go around and say, I get it, you can't refute it, and I'm kind of okay with it?
I wouldn't worship him.
No, I agree with that. That I could have guessed from the outset. But in that situation, where it's less like fairies, it's less like, ghosts, it's less of this crazy ideas.
Yes.
There's actually a logical sequence of words that can be given, meaning where there is a creator to this world. What do you say then?
Yeah, I agree. I'm intrigued by the thought that when you make a simulated world, and there are crude ones like Second Life.
Yes.
There has to be a physics built into it.
Yes.
And when you drop things, they fall, and when you throw them up and catch them, it works. But you can violate that physics. I mean, the pimply youth doing the simulation can somehow just at will change the physics, and you could suddenly fly, as you can in Second Life. It's got to be a pretty disciplined pimply youth that sees to it.
As a creator of this world should be, I would say.
Yes, but that we don't see that. Well, I suppose we don't. I mean, maybe.
Well, maybe he wipes our memory clean after playing around with us, right? All these things are possible.
Yes.
We can get a pretty good feel for the double slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment. Not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes and what's known as an interference pattern. So how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave?
Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave.
A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electrons